Our first example involves a collision between a jet aircraft and an airborne object. We want to determine the scalar and vector components of relative velocity in directions normal and tangent to a specified surface. We have previously used the dot product to resolve forces into components parallel and perpendicular to a line. When the decomposition is to be performed with respect to a line or axis, the dot product is the preferred initial operation. We get the parallel component first, then extract the perpendicular component from the total and parallel components. When, as in the present case, the decomposition is to be performed with respect to a surface, the cross product is the preferred initial operation. There are many vector orientations that can lie in the plane of, that is, be tangent to, the surface. Finding a desirable tangent component first is unclear. In contrast, there is a well-defined unit normal out of or into a surface, so using the cross product to find the normal component first is preferable, with the tangent component extracted after the fact from the total and normal components. We could then ask which unit normal is more appropriate, the one coming out of the jet surface or the one going in. Since the jet is overtaking the bird, with the bird's relative velocity coming at the jet at 250 meters per second, it seems more appropriate to use a unit normal going into the jet surface. Since we know the coordinates of A, B, and C, there are three different combinations of cross products that we could use to find this unit normal. One is not better than the others, and you can try different combinations after the fact to verify that it does not matter which one we choose. What does matter is that we use the right-hand rule to confirm that our choice results in a vector that goes into the surface of the jet. One appropriate choice is a unit normal resulting from RAB cross RAC. Our unit normal will be found first from unit normal equals RAB cross RAC divided by the magnitude of that vector. We will then proceed to find the normal and tangent components from V normal magnitude equals the velocity vector dotted into the unit normal, and normal velocity component will be normal velocity magnitude on the unit normal. The tangent magnitude will be the square root of the speed squared less the normal velocity squared, and the tangent velocity vector will be the difference between the velocity and the normal component of velocity vector. We now proceed to carry out these details. Our coordinates are RA equals 3I meters, RB is 1I, so I'll just write it as I minus 0.6J meters. And RC is 0.8K meters. Our relative position vector RAB is RB minus RA, and that ends up being minus 2I minus 0.6J meters. Our relative position vector RAC is RC minus RA, and that's minus 3I plus 0.8K meters. The direction of our unit normal is found from RAB cross RAC. And our components are minus 2, minus 0.60, and minus 3, 0, and 0.8. And we have in the I direction, we have 0.8 times minus 0.6, which is minus 0.48 in I. And in the minus j direction, we have minus 2 times 0.8. That ends up giving us a plus 1.6 j. And in the k direction, we have a minus 3 times minus 0.6, which gives us a net minus 1.8 k. And this has units of meters squared, since each relative position vector has units of meters. The magnitude of that vector we can find from the square root of the sum of the squares of its components, and that turns out to be equal to 2.456 meters squared. So our unit vector, normal to the plane, actually going into the plane, is RAB cross RAC divided by its magnitude, and when we plug the numbers in, we end up with minus 0.1955 I plus 0.6515 J and minus 0.733 K. The magnitude of the normal velocity is v dot un, and since we're given in the problem statement that the bird travels with a relative velocity of 250 meters per second in the minus x direction, we have that the normal velocity is minus 250 times minus 0.1955, and that ends up being equal to 48.87 meters per second. The normal velocity vector is that 48.87 meters per second on the unit vector, and that gives us 48.87 on our unit vector, and those values end up being minus 9.55 I plus 31.84 J minus 35.82 K meters per second. The magnitude of our tangent velocity is the square root of v squared minus vn squared, so that's 250 squared minus 48.87 squared, all of that square root, and that ends up giving us 245.2 meters per second. The tangent velocity vector is the difference between the velocity vector and the normal component, and that ends up being minus 240.5 I minus 31.84 J plus 35.82 K meters per second. In our final example, we need to find a minimum distance between a fixed point E and a surface defined by points A, B, and C. Such a minimum distance will be found from a line that goes through E and penetrates the surface perpendicular or normal to the plate. The point D, sketched on the plate surface, represents the penetration point of the normal line that goes through E, but we actually don't know yet where that is. How do we proceed? Here we have sketched a position vector from a known point on the plate A to the fixed point E. We have the information needed to find the relative position vector RAE. In addition, we can define a unit normal coming out of the plate using two relative position vectors in the plate to form a cross product. Let's call this UN. We can then find the magnitude of Rn by taking the dot product of RAE and UN. Recall that RAE dot UN would by definition be equal to the magnitude of RAE times the magnitude of the unit vector, which is 1, times the cosine of the angle between RAE and UN, which I've labeled theta here. But that is exactly the length of Rn that's sketched above. In fact, this looks remarkably similar to what we did in the previous example in terms of resolving a vector into components normal and tangent to a surface. The only difference now is that we are dealing with relative position vectors instead of relative velocity vectors. Perhaps one important difference is that we are looking for a unit vector that comes out of the surface instead of going into it. Again, there are three combinations of vector cross products that will give us an appropriate orientation. You should verify using the right-hand rule that the one selected here gives the appropriate orientation, but there are two other possibilities and one isn't any better than the others. We can see, for instance, that a unit normal could be defined from RCA cross RCB divided by the magnitude of that vector. Now you may also be wondering what is special about RAE. The answer is that there is nothing special about it. We could take the dot product between any relative position vector on the plate surface and the unit normal and get the same answer for Rn. As part of our solution, we'll verify that we get the same value whether we take RAE.UN, RBE.UN, or RCE.UN. We can now carry out the details. We can see that RCA is equal to 6I minus 8K inches, and RCB is equal to 10J minus 8K inches. We also have three relative position vectors of interest from the plate to point E. We have RAE is equal to 12I plus 12J plus 10K inches. RBE is 18I plus 2J plus 10K inches. And RCE is 18I plus 12J plus 2K inches. Our unit normal is defined from RCA cross RCB, and the components of the array here, the second row is 6, 0, minus 8, and the third row is 0, 10, minus 8. And if we carry out those crosses, we end up with 80I plus 48J plus 60K, and that has units of inches squared since each relative position vector has units of inches. The magnitude of that vector we get from the square root of the sum of its squares, and that number turns out to be equal to 110.9 inches squared. So our unit vector, which is RCA cross RCB divided by its magnitude, ends up being 0.7212I plus 0.4327J and plus 0.5409K. Now you should verify that we get the same value for the normal distance whether we use RAE.UN or RBE.UN or RCE.UN. The specific numbers here turn out to be 12 times 0.7212 plus 12 times 0.4327 plus 10 times 0.5409 for RAE.UN. RBE.UN will be 18 times 0.7212 plus 2 times 0.4327 plus 10 times 0.5409. And finally, we have RCE.UN, which is 18 times 0.7212 plus 12 times 0.4327 plus 2 times 0.5409. And if we carry each of these out individually, what we should find is that each of them ends up being equal to 19.26 inches. So we get the same result no matter which relative position vector we use from the plate to the point of interest. Finally, before we leave this chapter, we should say something about division. As with multiplication, we can think of a vector as being divided by a scalar or perhaps by another vector. We have many reasons for dividing a vector by a scalar. Every time we establish a unit normal by dividing a vector by its own magnitude, we divide a vector by a scalar. But is there anything meaningful that comes from dividing a vector by another vector? Although such a thing might be defined, we have no physically meaningful quantity that results from this operation. So from our perspective, there is no such thing as dividing a vector by another vector. We now turn to using vector resolution in orthogonal components to tackle a very important class of problems, 2- and 3-dimensional particle equilibrium.